All right, folks, we left off discussing, turn off my broken here. We left off discussing balancing chemical equations, and now we are moving on to what is a mole. So remember back in chapter 1, chapter 2, probably chapter 1, when we talked about SI units, mole was one of them. And at the time, I just said you just need to know this term, but now it is time. It's time to talk about what a mole is. And it's actually not that difficult. I want you to think of a mole as kind of a chemist's dozen. So when we use the word dozen, that is basically code for the number 12, right? So when we say mole, it should be the same, where it's kind of like code for the number 602 hexillion. So instead of having a dozen of something, like a dozen donuts or a dozen people or a dozen jelly beans, we have 602 hexillion, or 6.02 times 10 to the 23rd power of something, of a quantity, right? So mole just represents a number. Let's go ahead, I'm not even on the right tab here. All right. So a mole is an SI fundamental unit for the quantity of matter in a substance. All right, so specifically in chemistry, that means 602 hexillion atoms of something. Right? So we can also express that in scientific notation using 6.02 times 10 to the 23rd power. So this comes in handy when you are trying to calculate how many atoms or molecules of something exists in a given quantity, right? So chemists don't sit out and count that many particles. That would take a billion lifetimes. I think somebody actually did the math, and I don't think you'd ever be able to count out that many particles. So what we use instead is mole to mass conversions. And we use that knowing that the mass of 1 mole of an element is the same as its atomic mass. So I want you to think about this in terms of molar mass equals atomic mass, or molar mass is atomic mass, but it's in grams. All right, so molar mass in grams is the same as atomic mass in AMU, or in atomic mass units. So for instance, we have carbon. Its atomic mass is 12.01. So that's how many, it's the average mass of how many protons and neutrons are in that element. But we can also use that number if we use the grams unit with it instead of an AMU or a U. And we can use that to express its molar mass. So this number also tells us in grams how many or how much a mole of that substance weighs. So if we have 602 hexillion carbon atoms, it would weigh 12.01 grams. So that's how we use that information. So molar mass is the mass of 1 mole of a substance. In other words, 602 hexillion atoms of that substance, or 602 units of that substance. So you can apply this to a molecule as well. Here's another visual for you. So 1 mole, 1 mole is equal to 12 grams of carbon, which is equal to 6.02 times 10 to the 23rd, or 602 hexillion atoms of carbon. So all these things are the same. They're just different ways to express. Another example would be 1 mole of, okay, so 1 mole of carbon is that many atoms of carbon, which is 12 grams of carbon. Another example would be oxygen. 1 mole of oxygen equals 6.02 times 10 to the 23rd atoms of oxygen, or 602 hexillion atoms, which is equal to 6 grams of oxygen, or 16. So 16 grams is, or 16 is the atomic mass of oxygen, which we can also apply to its molar mass. Right, so et cetera, et cetera. As long as you know an element's atomic mass, you're able to calculate its molar mass, because it's the same thing. So let's do an example. We are going to convert moles in mass of a substance. So if we know that the atomic mass of iron is 55.85 on the periodic table, we can also say that its molar mass is 55.85 grams of iron per mole of iron. So 1 mole of iron, 602 hexillion atoms of iron, weighs 55.85 grams. Another way to express that would just be flipping this ratio. So the conversion factors for moles and grams of oxygen are, remember, oxygen exists in a diatomic state. So we take oxygen's atomic mass of 16 and we multiply it by 2 because we're talking about a diatomic molecule here, okay? So as long as we say 1 mole of O2 on the bottom, then it makes perfect sense because these units just cancel out. So the conversion factors for moles and grams of oxygen, O2, are 32 grams per mole, or 1 mole, 602 hexillion molecules of O2 per 32 grams of O2. So again, since we know that oxygen is naturally diatomic, we use O2 and 1 mole of O2 because that contains 2 moles of oxygen atoms. So let's take this information and let's actually use it in a calculation. So we want to know how many grams of iron and oxygen are needed to make 2 moles of iron oxide. So all this means is that when we balance our equation, remember before, go back to this page. All right, remember we had 2 molecules of iron oxide here, okay? 2 molecules of iron oxide. So when it asks us, all right, when it asks us how many grams of iron and oxygen are needed to make 2 moles of iron oxide, it just means that we have 2 molecules of iron oxide. So we know that it takes 4 atoms of iron, 4 atoms of iron and 3 atoms of oxygen to react together to make 2 molecules of iron oxide. So that same ratio exists when you talk about moles, because this is just talking about ratios. So if we know that 4 iron atoms are needed and 3 oxygen atoms are needed to react and form 2 molecules of iron oxide, we also know that 4 moles of iron, 3 moles of oxygen will react to make 2 moles of iron oxide. So let's take the conversion factor that we know for iron, and we will multiply it by this conversion factor, because what we want to do is cancel out these units. And we can do that by putting the unit that we want to solve for on the top. So we want to solve for grams of iron. So that's what we're doing first. So we multiply what we know is true. We've been given 4 moles of iron. We know that from our chemical equation that we balanced. And we multiply that by this conversion factor that cancels out moles of iron. And we're left with 4 times 55.85 grams of iron, which equals 223.4 grams of iron. So let's do the same thing for oxygen. We're going to take 3 moles of oxygen times its conversion factor of 32 grams of O2 over 1 mole of O2. So these are going to cancel out, moles of O2, and all we have to do is multiply 3 times 32 grams of O2, and that equals 96 grams of O2. So the answer is that we need to make 2 moles of iron oxide. The chemist needs 223.4 grams of iron and 96 grams of oxygen. And that is all I have for you. I will potentially make another video that will discuss molar mass calculations and possibly do some mole mass conversions, possibly a little bit later. So I will wait for feedback from you and just see how this video goes.